All right, everyone. So we've talked about quadratic equations in section 2.1. Moving on to section 2 of the chapter, we're going to take that quadratic expression, ax squared plus bx plus c, and look at it as a function of that variable that appears. Generally, it's x. We could technically have other variables, but x is sort of like our standard. So looking through the Moodle Notes file, you'll see that a quadratic function, is labeled g of x. And, a, b, and c are real numbers, just like we saw in the previous section. A can't be 0. And it lists underneath there that the graph of a quadratic function is something that we always call a parabola. So you've probably seen parabolas at some point in the past. There's some information about them. I thought before we dug into like the algebra side of this, we'd actually look at the graphs of a couple of these guys just so we have a frame of reference. So I'm going to use the two examples that are listed here. You'll notice I've got Desmos pulled up to help me generate a graph, which is, kind of standard. All right, let's take a look at this guy. So the first example we've got listed is y equals negative x squared plus 9x. All right, so this is kind of the general shape of a parabola here. It looks kind of, so you're saying, nice, curve that reaches like a peak or a valley, as the case may be. We'll talk about that in a moment, and then sort of, starts dropping back down. So the graph continues, off the edges of the graph, following the same direction that it's already going in. As usual, Desmos handily points out, sort of the x and y intercept. So there's one x-intercept. There's the other one. It's also the y-intercept. It also points out, sort of for this particular function, this peak point right here. So you see the 4.5, 20.25. Those are our coordinates for that peak point. That spot where we sort of go from rising to falling, or vice versa, we refer to as the vertex of the parabola. And you might notice we can sort of end up drawing in like a vertical line right here. I don't know why I'm talking about it like that. I could have Desmos draw the thing in just as well. So x equals 4.5. You'll notice now I've got this vertical line sitting right here, and what's on one side of the line is basically a mirror image of what's over on the other side. So this is what we will commonly call the axis of symmetry of the parabola. So, basically, if you've got the vertex, this vertical line cutting down through it, you can draw what's on one half and then just kind of flip it over to get the other half. So a couple of key, things to point out about a parabola is that the vertex in this instance is what you call a maximum for the thing. It's as high as this graph ever gets because it starts dropping after we pass by the vertex. And as it turns out, one can determine whether the vertex is a maximum or possibly a minimum. You could have what I refer to this as a sad parabola because it looks kind of like a frown. But you might also have a happy parabola that opens upward. We'll see an example of one of those in a moment. And as the notes mention, it turns out determining which way the parabola opens, up or down, is really just a matter of looking at this guy right here, the x squared term in your quadratic function. So looking at that guy right now, you see that the coefficient of that x squared term is a -1. It's negative. And if you take a look at the notes file, a leading coefficient in a, if you're following the ax squared plus bx plus c format, if that's negative, the parabola is always going to open downward. So the graph is always going to be like a sad parabola if that leading coefficient is negative. And the vertex in that instance will always actually be a maximum for this guy. All right, let me go ahead and get rid of that axis of symmetry. So here's an instance of one example of a sketch of a graph of a parabola. This isn't really a sketch because we had software do it. You could sketch this by hand relatively easily if you're able to identify where the vertex is, and then use that as you say, find like x-intercepts or y-intercepts, and then kind of connect the dots using that axis of symmetry as a guide. Give me just a moment here, and we'll take a look at another example. All right, I did a little finagling of the of the x-axis range that Desmos is showing us here to take a look at this next example, just so it's nice and framed up when we get started. So let's go ahead and sketch a graph of this second guy. So we have y equals x squared plus 4x plus 4. All right, so once again, it's nicely centered up, but this time around, if we look, there's not technically a coefficient listed right there, but as we've discussed before, you can sort of implicitly assume there's a 1 right there. 1 is a positive number, so our parabola opens upward. We've got a happy parabola this time around. And you'll notice, working this way, our vertex is called out by Desmos as -2, 0. It turns out that's actually our only x-intercept for this particular quadratic function. We do have a y-intercept that's kind of flagged out as 0, 4. If you were trying to sketch this by hand, you could use the location of the vertex and the axis symmetry and the y-intercept sort of to help you generate a graph. But this is getting across, sort of like the key point of the graph. We're opening upward. Our vertex is now a minimum, and you can still see x-intercepts and stuff called out. Finding x-intercepts, as it turns out, is something we've kind of already done, because if you'll recall, the x-intercept of a graph is where it crosses the x-axis, which means that y is equal to 0. So if we replace the y over here in our formula with a 0, and let me get rid of that 1. Looking at this, the y, replacing that y with a 0, you have 0 equals x squared plus 4x plus 4. That's the sort of quadratic equation we spent the entire previous section solving, right? So you can use, the quadratic formula or factorization, whichever way you want to go, to identify the coordinates of any x-intercepts. And it turns out this time, -2 is the only option. So we've taken a look at the graphs, but I did want to dig in a little more on the algebra side of this. In particular, I keep saying once you have the vertex, it's pretty straightforward to generate a graph. So I haven't really talked about how to get that vertex. And that's something that it turns out we don't even need to worry about having a tool sketch the graph for us. So long as we've got, the formula that's generating our quadratic function, we can find the vertex. And we will take a look at that next time.